Hi, this is Gordon Wade presenting my final project for CS89. So what I'll do is walk through these slides first, and then we can go and take a look at some of the code. So for this project, I chose to create a recommender system for recommending good beer. This is based on the technique of collaborative filtering, and we use the autoencoder architecture for our models. The dataset that we use is a set of quantitative beer reviews provided by Kaggle. So the technology that I used for this is very standard based on what we've been doing in this class. I used Python, Keras, and TensorFlow, and I have the specific versions listed here. And I was able to do all the training for this on my local setup, which is a MacBook Pro, though I do think you could significantly cut down on the training time by using a well-apportioned VM. So the data set that I used is provided at this link listed here, and it's comprised of 1.5 million beer ratings, and each of those records has the following fields. The main ones that we're interested in are the beer ID, which we use as a key to get the beer info at the end, and then the review overall, which is a 1 to 5 point scale of the user reviews. We also use the subcomponents aroma, appearance, palate, and taste for a brief portion of this project. So the installation and setup is very simple. I've been using a Conda environment for this class, and so I already had all the packages I need, but I've listed them out here along with the versions in case anyone needs to set up a virtual environment to come along with this. So the concept for this model is what's called collaborative filtering. And that is a useful technique that's used in a lot of recommender systems. Basically, it allows you to take a sparsely populated matrix in which you have a small amount of information about a lot of different users. Say you have tens of thousands of users like we do in this data set, and each one of them has reviewed somewhere between 1 and say a couple thousand different products, but none of them have reviewed all the products because our full set might be 50,000 or so. So what we do with collaborative filtering is try and understand the patterns that make up a user's taste and try to understand the similarity between users. And this way we are then able to predict what we think a user will review an item that they haven't had yet based on their similarity to other users. So this uses the autoencoder framework, which we learned about in this class. And as we know, this has a smaller hidden layer in the middle, which forms a bottleneck, and that bottleneck forces us to learn some generalized patterns, which we can then apply to our data. So one of the first things that we had to do in order to get this model set up is pre-processing. So the original data set contains a lot of extraneous information, and it is formatted with 1 row per review. What we want is to get rid of all the extraneous stuff and then convert our data set and pivot it so that we have 1 row per user. And at first, I tried to do this by using kind of the normal tools, importing it as a pandas data frame and using the pivot for that. But it turns out that our records are extremely large, and that because pivoting ended up creating a data frame of tens of thousands of rows by tens of thousands of columns, this was too big to fit in memory, especially with multiple copies as pandas uses. So we had to put a little bit more thought into how to actually do this pre-processing. But at the end, what we're doing is converting from the original records like we have on the left into the type of record we have on the right. And what that is a username on the left-hand column side and a set of beer IDs across the top with the 5-point overall score in the data area. All right, so about our model. I used just a basic autoencoder architecture and several different variations on this throughout the experiment. The size of the input and output layers is based on the number of unique beers that we have. And then we importantly did have to use a custom loss function. So it's a standard MSE function, but because we're predicting more outputs than we have inputs, we have to mask those and only compare the MSE to the data that we actually have in our input set. For some experimentation on this, I began with a simple shallow model encoder with just the one coding layer in the middle, and experimented with several different sizes here to see how that impacted the learning. I then saw that some publications have suggested that adding depth is a good way to improve your model, so I tried adding a few more layers to see how that affected our performance. And finally, as I mentioned at the datasets section, I used the subcomponents in order to see if providing more detailed input data would help us to generate better outputs. So for some of the code highlights, we ended up creating quite a lot of models for this project, and so I wrote several different functions to quickly generate these types of different models, and then also to train them and save the charts for the loss history of each of them. As I mentioned before, we used this custom loss function, and basically what this is doing is given our truth and our predicted data, if the truth data is 0, then we're not taking the prediction into account when generating our MSE. And that's because a 0 indicates that the beer has not yet been rated, as the actual scale is 1 to 5, and we don't want to train our model to just think that everything should be a 0 because the matrix we're working with is so sparsely populated. So here are some of our results. The first experiment that I did was to try several different coding sizes for the shallow autoencoder architecture. And what we can see here is that they actually all perform pretty well. And we can see the loss drops off quickly for all of these models. It turns out that varying the coding layer size in this network didn't actually make a huge difference. We can see a small difference between some of the bigger models with a little bit more overtraining occurring near the end, but the final loss is actually quite similar among all of them, and even the training time does not vary a lot based on just this. For the next set of the experiments, I created a few additional architectures with 3 and 5 layers respectively. And the main thing that stands out to me is that the training time decreases a lot for our saturation point. So we can see that the curve on those deeper models is much, much steeper than on the shallow model. And we can also see that the deeper models are a little bit more susceptible to overtraining near the end, which is expected as they've kind of hit the saturation point earlier on. But ultimately, the loss ends up being quite similar between these and the simple shallow model again. Finally, the last thing I did was to incorporate those other subcomponent weights that I mentioned at the beginning. So there's the overall score, and then there are 4 different subcomponents that people are allowed to rate as well. And we can see here that the curve is actually much shallower when we include those components versus the deep model or the original model. And we can see that the overtraining becomes much more pronounced, especially near the end. But again, the overall loss doesn't actually decrease. In fact, if anything, it may get a little bit worse. So what this suggests to me is that incorporating the component scores tends to differentiate users a little bit more in a way that's not helpful. And so what we're really doing is just memorizing information about individual users instead of learning generalizable techniques. So that's probably not the best approach. The output of this project is that we can take a username from anyone in our data set, the test or training data, along with that data frame and the model that we'd like to use. And then what we'll do is generate some predictions for them, remove the beers that they've already rated, and then choose the top rated beers out of the remaining ones. And here we provide that info back to the user, the brewery, the beer name, and the beer style. And so with this example, which is just one of the first reviewers in the data set, we can see that we're recommending actually some pretty consistent styles, which I think is a good indication that the model may be working well. So to summarize, we demonstrated that we can create a recommender system using collaborative filtering and the autoencoder architecture. And we learned that varying the coding layer, the size of the coding layer, doesn't have a huge effect. It may have a little bit of an effect, but it's not huge. We demonstrated that adding depth to our model can decrease the training time, but that the final loss remains pretty similar. And we showed that adding width to our model in the sense of the input data being much wider does not actually provide us with information that's useful in this setting, though it might be helpful in a different setting. So for challenges and future directions, I think there's a lot left to explore here. As I noted before, one of my challenges was that big data sets that are also sparse can be really hard to manipulate. And I think there are probably more elegant solutions than the one I came up with, so that might be something that's worth looking into. I also was curious about evaluating the model's performance, so I think that MSE is a pretty good metric to start with, and the custom masked MSE that I used for this seems reasonable, but I was wondering if there might be a better way to measure that. So I think that would be something worth looking into. In terms of future directions, I think there's a lot left to explore with this type of data set. So just in the vein of creating a recommender system, a lot of recommender systems use content-based recommendation in addition to or instead of collaborative filtering. And the difference here is that collaborative filtering is based on creating a model of users and user similarity, whereas content-based recommendation is based on actually understanding something about the product that you are recommending and what makes products similar. The other thing that I was personally interested in doing was compiling some text reviews of these beers and seeing if we could cluster them or compare their similarity using a tool like Doc2Vec or Genzim, like we explored in this class a little bit. So I think it would be very interesting to use one or more of the above to kind of cluster our data and just see what we can learn about how these different sets of beers fit together. And with that, let's go ahead and take a look at some of the code. All right, so here we are. This stuff up here is just all the regular pre-processing that I kind of already mentioned. One thing I didn't include yet was that setting the data types as you import the data can actually help a lot in decreasing the memory footprint and allowing you to manipulate it more easily without consuming a lot of resources. So here's the section in which we reshaped our data. And what I ended up doing here, because a pivot was taking up way too much memory and was basically crashing out, is that I figured out how big our new sparse data frame would be, meaning one row for each unique user and one column for each unique beer. And I created a data frame of this size, which I then populated by looping through our existing data. As I said, it's probably not the most elegant solution, but it certainly gets the job done, and you end up with something like this. To set up the model, this should look pretty similar. It's basic Keras like we've been using throughout this course. We split up the data into test and training and normalize it so it's on a 0 to 1 float scale. This is the simple shallow autoencoder, which is very much like some of the autoencoder architectures we've already used. And the only things that we really set, we have a constant for n being the number of unique products that we have, and then we set the coding dimension here. And that's the thing that we varied in the first experiment. Here's the custom loss, so I talked about that a little bit already, but basically it ignores any data that the user has not yet provided when calculating the MSE. And of course, here's just a normal training function and functions to save each model and plot and save the history so that we don't have to train these models so many times. So here's our exploration of deeper models, and we can see here we're adding another layer here and running it with similar parameters. Here we see what I just showed in the PowerPoint. And here we have another one with some extra layers too. And as I mentioned before, that basically steepens out this part of the curve. And we start to see overtraining a little bit earlier on, which really means that we could probably stop training this around like 20 epochs or so instead of 100. For using additional information, this is the information that I was talking about. So for each rating, we have an overall review, and then we have a specific subcomponent review for these 4 different categories. And so we did basically the same type of pre-processing here. So now we have a data frame that's 5 times as wide as the original because we have 4 additional categories multiplied by each unique item. And down here we have an autoencoder, which we train with the input wider to accommodate for that. But we keep the output layer as narrow as the original was because we just want to produce one overall score for each item. And here we can see, as I said, that this actually does not help our performance at all, and it takes significantly longer to train, so much worse, in my opinion. And then for the last part, actually generating our recommendations, what I did was create a subset data frame from the original that just contains the beer facts. And so this beer ID is a primary key, basically. And all we really need is the name of the brewery, beer, and style to provide that to our user. So here we have a couple of functions that just take in the model that we'd like to use, the original data frame with all of our reviews in it, and the username that we'd like to get recommendations for. We get the masked prediction, and we get the top 5 results from that, and then we return them and print them out to the user. So that is about it